One day, far in the future, every star you see will go dark. Not next year, not in 1,000 years, but in a span so large that our numbers strain to hold it. The universe, which feels busy and bright today, will grow quiet. Welcome to the Drowsy Astronaut. Here we take time to move slowly through the universe, looking at big questions in a simple way. This is a place where science turns into a calm story, something you can follow while you relax and maybe fall asleep. And even if you drift off, your mind will keep traveling through space and time with the story. So let's begin. The idea at the center of tonight's journey is called the heatdeath of the universe, a phrase that sounds fierce, yet points to something very calm. It is not an ending with fire, it is an ending with balance. Energy that is uneven today becomes even later, and once the differences fade, nothing new can happen. We are going to walk toward that idea slowly, step by step, starting from what you already know. If you pour a hot drink and set it on the table, it cools. If you take ice from the freezer and leave it in the room, it melts. Heat flows from hot to cold, it spreads. It evens out. You do not see your tea grow hotter on its own. You do not see ice freeze itself without help. This simple rule is the second law of thermodynamics, a long name for a familiar truth. Now stretch that truth from your kitchen to the cosmos. Stars are hot, space is cold, so energy flows outward. Galaxies shine, their light crosses the darkness, and slowly the edges soften. As ages pass, the differences shrink, the bright becomes dim, the hot becomes warm, the warm becomes the same as everything around it. When the differences are gone, there is no way to power change, and the universe rests. That resting state, quiet and even, is what physicists call heat death. This sounds abstract, but it helps to tie it to things you know. Think of your home at night, lights glowing in a few rooms, others dark and quiet. If you leave the doors open long enough, warm and cool air mix, sounds settle, and the whole place becomes still. The universe is like that, but on a scale so large that our minds have to move slowly to meet it. Right now, the universe is not still, it is alive with difference. Stars burn, galaxies collide, black holes feed, planets glow with reflected light. Everywhere, energy moves, turning gradients into motion, motion into light, and light into warmth. We live in what scientists call the stelliferous era, a long age when stars are the main engines of change. This is the age of fire, the age of light, the age that gives us night skies full of points. A star is a furnace that turns hydrogen into helium, releasing energy as it goes. The bigger the star, the faster it burns, the brighter it shines, the shorter it lives. Small stars burn slowly, dim but steady, lasting for trillions of years. Our sun sits in the middle, neither fast nor slow, with a total life of about 10 billion years, and roughly half of that is already behind us. Imagine a city lit by lamps of all sizes. The biggest lamps blaze, they draw your eye, and they empty their oil quickly. The smallest lamps sip their fuel, they glow softly, and they last long after the brighter ones have gone out. In the universe, the large blue stars are the short-lived lamps, the tiny red dwarfs are the slow-burning candles. When the busy city grows old, only the small steady lights remain, and then, much later, even they fade. Over very long stretches of time, the crowd of stars thins. First the giants go, then stars like our sun, and at last the tiny red dwarfs, which glow so gently that they outlast almost everything. If you could step forward far enough, you would see a sky that is no longer crowded with bright constellations but scattered with dim red points, each one a last ember in a cooling fireplace. Wait longer still, and even those embers turn black. The idea may feel heavy, so let us lift it with a different view. To know that the fire will end teaches you to see how bright it is now. You live in a universe that is young enough to have stars in every direction, galaxies by the hundreds of billions, and light in every night. Saying that the heat death waits far ahead is also a way of saying that you and I exist in the lively chapter, the chapter filled with flame and motion. That is not a reason for worry, it is a reason for quiet wonder. Still, the story asks us to keep walking. Stars do not simply blink off, they end in different ways, depending on their size. The largest run out of fuel and collapse, their cores squeeze into neutron stars or into black holes, while their outer layers rush outward as supernovae. Medium stars like our Sun swell into red giants, shed their outer shells, and leave behind white dwarfs, hot and dense, slowly cooling over unthinkable time. The smallest stars, the patient red dwarfs, simply dim, settle, and fade. Each ending moves energy outward. Each ending makes the universe a little more even. White dwarfs will glow for eons, slowly radiating away their stored heat. If you set a white hot metal bar on a winter night, you know it cools steadily. It does not hold its heat forever. A white dwarf is like that bar, except its night is the cosmos, and its timescale is billions to trillions of years. When its heat is gone, it becomes a black dwarf, a body that holds mass but yields no light. That quiet cooling is part of the great evening out, part of the long approach to balance. When people first hear heat death, they sometimes imagine a universe ending in flames. It is the opposite. It is the end of useful differences, the end of strong gradients, the end of work. Work in physics is not paperwork or chores, it is the name we give to change driven by differences. A wheel turns because one side is higher than another, water flows because one place is higher than another, heat flows because one region is hotter than another. When there is no higher and no lower, no hotter and no colder, the wheel rests, the river stops, the glow fades, the universe does the same. How far away is this? Far beyond any human calendar, far beyond the age of countries, languages, species, even far beyond the life of stars. We measure the history of our world in thousands of years, the history of stars in billions, the quieting of the cosmos in numbers that carry thousands of zeros. The scale is so large that your job, here and now, is not to count, but to feel how small our moment is, and how precious light is while it lasts. To keep the path simple, return to the second law. It says that if you have two regions at two temperatures, they will exchange heat until they match. The universe began very hot and very dense, then it expanded and cooled, and that expansion continues. Space grows, light stretches, energy thins, differences smooth out. On this moving stage, stars form as pockets of gas collapse. They burn for a while, then they pass their energy back into space. The great account book of energy is simple, the entries are steady, and the final balance is evenness. You can see a smaller version of this in your own day. Breakfast gives you energy, you move, you work, and slowly the energy spreads into heat, into motion, into little differences that settle by evening. Night comes, and the room grows quiet, and you rest. The universe has a similar rhythm, but its day is billions of trillions of times longer. It began with a burst, it moved into a long, busy afternoon of stars and galaxies, and in the far end, it will rest. Why call this heat death if it is peaceful? The name is old, it comes from the language of steam engines and early thermodynamics, when scientists were learning how heat becomes work and how work becomes heat. The key is not the word death, the key is the word heat. Heat is the form energy takes when difference fades, when motion becomes jumbled, when order gives way to spread. In that spread, there is no way to lift a weight, no way to run a clock, no way to spark a star. If you have ever wound a toy and watched it spin, you know that the spring unwinds, the motion slows, and the toy stops. The universe is not a toy, but the idea is related. The early cosmos had strong gradients, it had a lot of wound-up potential, and as time passes, those gradients soften. Stars offer flashes of brightness, galaxies create structure, but the trend is downward toward evenness. Let us pause on red dwarfs again, because they carry a gentle lesson. They burn their hydrogen so slowly that they will still be shining when all the grand bright stars have gone, and yet their patience does not change the final outcome. It only stretches the timeline. Think of a library filled with candles. The tall candles flare and finish fast. The small ones glow faintly for a very long time. One day, long after, the last small flame will go out. The room will not end with a bang, it will end with a long, soft exhale. That is the feeling of the heat death. Another part of the story comes from gravity, which fights against spread by pulling things together. Gravity builds stars from gas, it builds galaxies from stars, it builds clusters from galaxies. You might wonder, if gravity gathers, why does the universe still head for evenness? The answer is that gravity can create pockets of order, but it cannot stop the overall trend. Those pockets still radiate heat, they still move energy outward, and in the end, their fuel still runs out. Gravity is the great builder, thermodynamics is the quiet accountant, and the accountant keeps the final tally. There is a comforting way to hold this. Balance is where everything rests after a very long day. The universe does not end in anger, it ends in stillness. That stillness is not a punishment, it is the calm at the far edge of time. If that makes your heart feel heavy, remember that you live in the lively part, surrounded by stars, carried by a warm planet, traveling through a galaxy that still glows. You are here during the fire, not during the quiet. Now bring the idea closer to your hands. Take a metal spoon from a cup of hot tea, hold it for a moment, feel the warmth move. Heat flows into your fingers, the spoon cools, the air warms a trace, everything seeks the middle. If you wait, the spoon will feel like the room. That simple feeling is the same principle at the scale of galaxies. The difference becomes smaller, the flow becomes weaker, the system creeps toward rest. This is why the phrase time's arrow is tied to entropy, the measure of spread. You know which way time points because you can tell which cup is hotter, which ice cube is melting, which candle is burning down. In a universe at heat death, there are no candles, no melting ice, no fresh cups. There is no strong arrow to follow. The story does not break, it simply stretches so thin that new chapters can no longer be written. What happens to the things left behind? White dwarfs cool into black dwarfs. Neutron stars sit as dense city-sized spheres, slowly losing any spare heat. Black holes persist, holding what they have swallowed, then in a timescale so long it sounds like fiction, they quietly leak energy through a quantum process called Hawking radiation. That part of the story comes later in our journey, yet you can sense how every path points the same way, toward less difference, toward more evenness, toward rest. If you step outside late at night, breathe, look up and let this sink in, something gentle happens. The sky is not only a set of stars, it is a record of a universe doing work. Every star is a gradient engine. Every beam of light is energy moving from where it is concentrated to where it is thin. You are watching the second law drawn across the darkness, and you are doing it during the bright noon of cosmic time. You do not need equations to feel this. You only need patience and a willingness to let large scales move through your thoughts. If big numbers feel slippery, let them be. You can still hold the shape of the story. Early differences, power motion, motion spends difference, the spending slows, and a long quiet arrives. In a way, the heat death is the simplest ending possible. Not a clash, not a storm, just the leveling of every hill, the smoothing of every ripple, the soft closing of every door. The universe that began with a tremendous start ends with a pause that becomes permanent. Between those two lies everything you love, from the first stars to planets to oceans to life, to minds that can ask these questions while lying in bed. Because this is part 1, we will keep our footing here at the beginning of the long descent. We have met the second law. We have seen why stars cannot burn forever. We have walked among red dwarfs that outlast their brighter cousins. In the parts to come, we will move further, through the eras when white dwarfs cool, when galaxies thin, when black holes rule, and when even they fade. We will take each stage slowly, with clear steps, so that by the end you will carry the whole arc in your mind as a simple, steady picture. For now, rest with this thought. The universe runs on differences, and differences run down. You live in the moment when the differences are rich, when the engines are many, when the sky is full. Knowing that it will not always be so does not spoil the view, it sharpens it. It turns the night into a treasure and the simplest star into a gift. If the idea still feels too large, bring it back to something small. A room in evening, the day finished, the air settled, the lights low. The quiet that follows is not empty, it is full of the day's echo. It is the natural rest after motion. The heatdeath is the universe's version of that feeling, a quiet that holds the memory of everything that came before. Stars, for all their brilliance, are temporary furnaces. They shine because they are burning fuel, and like every fire, they have a beginning, a middle, and an end. What makes them extraordinary is not that they fade, but that they fade on timescales so vast that human history feels like the blink of an eye beside them. When a star finishes its life, it leaves behind not only silence, but a footprint that marks the path toward the universe's long decline. Take our sun as an example. Right now, it quietly fuses hydrogen into helium in its core, releasing light and warmth. For billions of years, it has done this without pause, and for billions more, it will continue. But slowly, the balance changes. The hydrogen at the center grows scarce, helium ash piles up, and the furnace stutters. When the fuel runs thin, the sun will swell outward into a red giant, engulfing Mercury and Venus, and perhaps brushing Earth with waves of unbearable heat. Its outer layers will drift away, forming a glowing shell of gas, while its core collapses into a white dwarf. That white dwarf, small and dense, will shine faintly for trillions of years until even its glow fades. The same is true for stars of many sizes, though the details differ. Massive stars end with drama, collapsing into neutron stars or black holes after titanic supernova explosions. Smaller stars end more quietly, turning into dim embers. But in every case, the pattern is the same. Fuel is spent, energy is released, remnants are left behind. Over time, those remnants cool, their energy thins, and they add to the evening out of the cosmos. Imagine again the city lit by lamps. First, the brightest streetlights go out, exploding in showers of sparks. Then the steady lanterns dim, shedding their covers and leaving glowing metal at the center. Finally, only the smallest candles remain, flickering patiently, holding on for longer than anyone expected. In the end, the whole city grows dark. This darkness does not mean nothing is left. White dwarfs still drift, neutron stars still hum with gravity, and black holes still warp the space around them. But light, the great marker of activity, grows rarer and rarer. The universe shifts from a place of blazing brilliance to one of quiet endurance. Scientists estimate that the stelliferous era, the age of stars, will last for about 100 trillion years. To us, that number feels absurd. Our species has existed for only a few 100,000 years, our recorded history for only a few thousand. 100 trillion years stretches so far beyond that, it may as well be forever. Yet on the scale of the cosmos, even this long era is temporary. Eventually, star formation will slow, fuel will run low, and the age of stars will close. What comes after is a new chapter in the universe's decline, sometimes called the degenerate era. The name may sound harsh, but it simply refers to the kinds of objects that remain. Instead of stars blazing with fusion, the cosmos will be filled with remnants. White dwarfs, neutron stars, black holes, and planets stripped of their warmth. These are the leftovers, the husks, the survivors of stellar fire. Picture a landscape after a great fire. At first, the blaze lights everything, consuming wood, grass, and air. Then, when the flames are gone, the field is quiet, covered with ashes and charred remains. The energy has been spent, the heat released, and what lingers are the relics. That is what the universe becomes once the stars are gone, a place of remnants, cooling slowly into stillness. Even so, the story is not dull. White dwarfs, for example, are fascinating objects. Imagine something with the mass of a star squeezed into a sphere the size of Earth. Their gravity is so intense that matter is packed into exotic states, atoms stripped bare, electrons locked in strange quantum pressure. For trillions of years, they radiate heat, slowly fading from white to blue to red, until at last they become invisible black dwarfs. Neutron stars are stranger still. A ball of matter so dense that a teaspoon of it would weigh more than a mountain. Born from the collapsed cores of massive stars, they spin rapidly, sometimes hundreds of times a second, their magnetic fields sweeping beams of radiation across the cosmos. These are pulsars, cosmic lighthouses flashing as they turn. Over immense spans of time, even their rotation slows, their beams fade, and they too join the quiet. And then there are black holes, the most enduring remnants of all. When a massive star collapses fully, it forms a region where gravity is so strong that not even light can escape. Black holes do not shine, but they shape their surroundings. They devour matter, they merge, they stir space itself. Long after stars are gone, black holes will remain, scattered across the universe like great anchors of gravity. But even they will not last forever. Over unimaginable spans, they too will fade through a subtle quantum process, evaporating into the void. Planets, moons, and asteroids also persist, drifting silently. Without the heat of their stars, they freeze, their surfaces locked in eternal cold. Gas giants like Jupiter will remain as frigid balls of frozen gases. Rocky worlds like Earth will become silent stones. Their warmth, if any, will come only from the slow release of radioactive decay, a faint glow that dwindles with time. When you add all of this together, the degenerate era is not bright, but it is not empty either. It is filled with husks, relics, leftovers of brighter times. White dwarfs cooling in silence, neutron stars fading, black holes brooding, planets drifting, a cosmos still full of matter, but lacking the vibrant energy that once made it sparkle. Pause for a moment and think about that scene. A sky with no stars, only faint embers if you are close enough to see them. Vast stretches of space where galaxies are invisible, their structures broken down, their light gone. It is a universe that feels abandoned, yet it is simply the natural path of energy evening itself. For those who lived earlier, like us, the thought is sobering. We see a universe full of light, and we forget how rare this moment is. For those who might exist in that far future, the sky would tell a different story. A story not of blazing fire, but of quiet remains. The same laws guide both views. Energy flows, differences fade, the balance grows nearer. But this does not mean nothing of interest happens in the degenerate era. Black holes continue to merge, sending ripples of gravity across space. White dwarfs may collide, igniting briefly in rare explosions called Type Ia supernovae, even after most stars are gone. Planets may be thrown from their systems by chance encounters, drifting as rogues through the dark. Though the universe grows quieter, it is never completely still. Still, the trend is clear. With every collision, with every fading glow, the differences shrink. And once the differences shrink far enough, entropy climbs higher and the path to heat death continues. It may help to return to the kitchen analogy. Imagine you have a cup of hot water and a cup of ice water. At first, the difference is strong, heat flows quickly. Over time, the difference shrinks, the flow slows, and finally both cups sit at room temperature. The early universe was like the two cups far apart in heat. The degenerate era is like the last stage, where the temperatures are nearly the same and only a faint trickle remains. By this point, trillions upon trillions of years have passed. Galaxies have gone dark, stars have burned out, and only remnants endure. If any beings are around to watch, their view will be strange indeed. No constellations, no galaxies glowing in the distance, only blackness, broken occasionally by a faint glow or a flash from a rare collision. For them, the idea of a bright sky full of stars would seem like legend. And yet, the story does not end here. Even remnants fade, and even black holes have lifespans. But those lifespans stretch beyond any scale we can truly imagine. Quadrillions, quintillions, numbers so large they feel unreal, and yet physics follows them patiently. Step by step, the long march continues. The remnants of stars, though quiet compared to the blazing youth of the cosmos, still carry weight. White dwarfs glow faintly, neutron stars spin in silence, and black holes sit as anchors of gravity. But the most fascinating of these survivors are black holes, because while everything else fades step by step, black holes hold on stubbornly, bending space itself around them. A black hole begins as the corpse of a massive star. When its core collapses under gravity, no force can resist the fall, and all of the mass is squeezed into a tiny region where density grows beyond comprehension. Around this region lies the event horizon, a boundary from which nothing, not even light, can escape. From the outside, black holes appear dark, invisible against the background, revealed only by the way they pull on nearby matter. If a black hole passes through a region filled with gas, it feeds. Matter spirals inward, heating as it falls, shining brightly just before vanishing into the dark. Entire stars can be torn apart this way, ripped into streams of gas that whirl into the black hole like water down a drain. In the earlier ages of the universe, when galaxies were crowded, these events were more common. Black holes sat at the hearts of galaxies, swallowing matter, powering quasars that shone brighter than anything else in the cosmos. But as time stretches, galaxies quiet. Stars fade, fuel thins, and the fireworks of feeding become rare. Black holes remain, but they grow still, sitting in emptier and emptier space. Their hunger does not stop, but there is less to consume. Eventually, they are like wells in a desert, waiting, yet finding nothing to drink. You might think this makes them eternal, but physics whispers otherwise. In the 1970s, Stephen Hawking showed that black holes are not completely dark. Quantum mechanics, the rules that govern the very small, predicts that black holes leak radiation, a slow and steady trickle of energy that seeps from their edges. This is called Hawking radiation, and it means that even black holes evaporate, given enough time. The process is slow, unbelievably slow, especially for large black holes. A small black hole might evaporate in a flash within a short cosmic span, but the giants at the centers of galaxies take timescales so immense that numbers strain. A black hole with the mass of the Sun would need about 1067 years to evaporate. That is a 1 followed by 67 zeros, longer than the entire age of the universe so far by a factor so large it is difficult to hold. Supermassive black holes, millions or billions of times the Sun's mass, last even longer, with lifespans of 100 years or more. To picture such times, think of writing a single digit every second for as long as you live. Even if you lived for the age of the universe itself, you would barely scratch the surface of those numbers. And yet, physics does not flinch. It says clearly that even these titans fade, slowly radiating away their mass into the void. What does it mean when a black hole evaporates? Imagine a block of ice left outside. At first it seems solid, unmoving, permanent, but in the warmth of the air it thins, drips and shrinks. A black hole is like that ice, except the warmth is not air, but the quantum froth of space itself, and the dripping takes place over time spans that dwarf imagination. During the degenerate era, when stars are gone and only remnants remain, black holes will rule as the heaviest objects. They will shape the orbits of lonely planets, they will tug on scattered matter, they will merge with one another, sending waves of gravity across space. But as the eons pile up, even they will begin to leak, drop by drop, until nothing of their gravity remains. The evaporation of black holes is the slow final act of structure. White dwarfs fade into black dwarfs, neutron stars cool, planets freeze, and at last the black holes themselves vanish into radiation. With their passing, the universe loses its last great giants, leaving behind only particles drifting in the vastness. This stage of cosmic history has been called the black hole era. It is a time when nearly all matter is locked up in black holes, waiting. The smaller ones vanish first, the larger ones endure, but eventually all share the same fate. The universe grows emptier, its structures unravel, and space itself becomes thinner in meaning. Pause for a moment and try to hold the image. A universe where galaxies no longer shine, stars no longer burn, planets no longer orbit, and only black holes drift. A dark sea, dotted not with light, but with invisible pits of gravity. If you could see them, it would be like staring at a field of silent wells, each one sitting, each one waiting. That is the black hole era, the long middle passage between the fading of stars and the final resting of all things. It is worth asking why this story feels heavy, perhaps because we are creatures of light, and the thought of its absence touches something deep. Yet there is another side. The endurance of black holes shows the patience of the universe. They hold on far longer than stars, far longer than galaxies, stretching their existence across spans so long that everything familiar has already passed. They are the last keepers of matter, the final stage of collapse, carrying the memory of stars long gone. When they do fade, the universe moves into its quietest age yet, sometimes called the dark era. In that age, no stars, no remnants, no black holes remain. Only particles, spread thinly across space, drifting endlessly. Photons, neutrinos, electrons, protons, the smallest building blocks, separated by distances so vast that they never meet again. This may sound like the end, but it is simply the next step in balance. Entropy continues to climb, differences continue to vanish, and the cosmos becomes smooth. In such a universe, time itself feels different. Without events, without change, time is no longer measured by the ticking of stars or the cycles of planets, but by the endless drift of particles in silence. The thought may make you uneasy, but it can also bring calm. The heat death is not violent. It is not an explosion, not a tearing apart. It is rest. The universe settles, evenly, smoothly, permanently. Even so, the path to that rest is long, and the chapters we have walked so far, the age of stars, the age of remnants, the age of black holes, are only part of the story. Ahead lie questions about what it means for time to stretch into stillness, and whether something unexpected might stir even in that balance. But those are thoughts for later steps. For now, the picture is simple. Black holes endure, then fade. The universe shifts from fire to husks to dark wells, and finally to silence. When the black holes have finally faded, the universe enters an age unlike anything before it. No stars shine, no remnants glow, and no wells of gravity linger to gather matter together. What is left is a thin, quiet ocean of particles, drifting through space that feels more like emptiness than structure. This stage is sometimes called the dark era, and though its name sounds final, it is simply another phase in the long path toward balance. The building blocks of matter remain. Protons, electrons, neutrinos, and photons move endlessly, spread thin across unimaginable distances. But the difference lies in how far apart they are. In the earlier universe, matter gathered into stars and galaxies, forming clusters and structures, islands of light in the sea of darkness. In the dark era, those islands dissolve. The ocean is flat, the ripples have smoothed, and what remains are particles so widely separated that they rarely, if ever, meet. Think of a vast desert, where grains of sand lie scattered across a field that stretches farther than you can see. Each grain is alone, surrounded by emptiness. The desert may be made of many grains, but its surface feels empty. That is the universe in the dark era. It is not nothing, but it is close enough to silence that the difference hardly matters. What happens to protons in such an age is still an open question in physics. Some theories suggest that protons, the stable cores of atoms, may not be eternal. Over timescales that dwarf even the lifespan of black holes, they might slowly decay, splitting into lighter particles and radiation. If this is true, then even the matter that makes up everything around you, the chair, the floor, your own body, is temporary, destined to fade into simpler pieces. The possible decay of protons would stretch across spans of at least 1034 years, and perhaps much longer. That is one followed by 34 zeros. To put this into perspective, the current age of the universe is only about 13.8 billion years, or 1.38 Gauss 1010. The gap between those numbers is so large that it feels impossible to picture. And yet, on the scale of the cosmos, such numbers are just steps along the path. If protons do decay, then the dark era grows even darker. Matter itself dissolves into radiation, leaving only lightweight particles, photons, neutrinos, and electrons drifting endlessly. If protons do not decay, then matter remains, though scattered so thinly across the void that its presence hardly breaks the stillness. Either way, the direction is the same, toward greater evenness, toward higher entropy, toward the quiet of balance. It is strange to think of a universe so thin. Right now, space may feel empty to you when you look at the night sky, but in truth, it is full of galaxies, clusters, and hidden matter. The dark era is emptier by far. Galaxies gone, stars gone, black holes gone, only particles left. Each one separated by distances so large that they might as well be alone forever. Imagine standing at the edge of a wide plain at dusk, watching the lights of distant towns flicker out one by one. At first, the landscape is dotted with glow, but then each light disappears, until the plain is nothing but darkness. That is the universe after eons of fading, when the last sparks are gone and only silence spreads. What does time mean in such an era? Without stars to burn, without galaxies to spin, without black holes to feed, the usual clocks of the cosmos are gone. Time does not stop, but it stretches differently. It is marked only by the endless drift of particles, the fading of energy gradients, the quiet thinning of differences. Time becomes a soft horizon, one that stretches so far that it ceases to feel like motion and instead feels like stillness. Even so, the laws continue. Entropy climbs, differences smooth out, and balance deepens. The second law of thermodynamics is patient, and it does not care whether it acts on cups of tea or on galaxies. In the dark era, its work is nearly finished, but the last small flows still occur, the last faint ripples still even out. If you try to picture this universe, the image may feel unsettling, a place with no light, no structure, no familiar forms. But there is also a strange peace in it. The dark era is quiet, not violent. It is not an explosion, not a tearing apart, but a soft settling into stillness. It is the long rest after an even longer day. And yet, even in this emptiness, subtle questions remain. If protons decay, then matter dissolves entirely. If they endure, then faint particles of matter drift forever. In both cases, the overall picture is balanced, but the details tell us how deep that balance goes. Scientists continue to study this because understanding the fate of matter is part of understanding the fate of the cosmos. It helps to return to something smaller, to see the same idea. Picture a campfire at night. First the flames dance, then they shrink to glowing coals, then the coals fade to ashes. Even when the fire is gone, the ashes remain, faint and quiet. The dark era is like those ashes. The fire of stars has gone, the coals of remnants have faded, and what remains is still matter, spread thin, but not vanished. Over stretches longer than we can hold, the dark era becomes all that is. No bursts of light, no new structures, no familiar clocks, only drift, only silence, only evenness. The story of the heatdeath moves forward, patient and calm, carrying the universe into its quietest chapter yet. The strange part is this: for all its silence, the dark era is not the end. Time does not stop, entropy does not halt, and physics continues its slow accounting. What seems like stillness is still motion, stretched thin across impossible spans. The story continues, with balance deepening step by step, until even the particles themselves face their final question. In the dark era, the fate of the cosmos begins to hinge on the smallest details. Large structures are gone, stars have burned out, black holes have evaporated, and what remains are the tiny pieces of matter. Protons, electrons, neutrinos, and photons drift through space that is quiet and thin. Whether the story stretches on forever in this form or dissolves further depends on what happens to protons. Protons are the building blocks of atoms. Every atom of hydrogen carries one, every atom of carbon in your body contains 6, every molecule of water is shaped around them. In our world, protons seem eternal. They do not decay in the span of human lifetimes, nor in the span of stars. But physics is not yet sure whether they last forever. Some theories suggest that protons are stable for eternity, that they will drift endlessly, never changing. If this is true, then the dark era remains filled with scattered matter, thin but lasting, tiny islands of substance surrounded by emptiness. Other theories suggest that protons have a half-life so long that it dwarfs all other timescales. If that is the case, then protons eventually decay, dissolving into lighter particles such as positrons and photons, until even the foundation of atoms is gone. The difference between these two paths is subtle on human scales, but enormous on cosmic scales. If protons endure, the universe will always have matter, even if it is too thin to gather. If protons decay, then eventually the universe becomes pure radiation, a sea of light particles spread across infinity, without a single atom left intact. To picture proton decay, it helps to return to something more familiar. Imagine an ancient stone, weathered by time. To your eye, it seems solid, permanent, unmoving. But rain falls, winds erode, and over thousands of years the stone crumbles, grain by grain. On scales of days, the stone seems eternal, but on scales of millennia, it changes. A proton is like that stone. Over spans of stars, it feels eternal, but over spans of 1034 years or more, it might crumble. Scientists search for signs of proton decay in underground laboratories, where giant tanks of water are watched for tiny flashes of light. Each flash could signal a proton dissolving into other particles. So far, no decay has been seen. This tells us only that if protons do decay, their lifetime is longer than 1034 years, a span already far beyond anything else we know. Whether they truly last forever, or whether their decay is simply slower than our patience, remains uncertain. If protons decay, then the dark era becomes even darker. White dwarfs and neutron stars, already cooled and silent, would crumble into lighter particles. Planets, asteroids, even the cold husk of Earth would dissolve. Bit by bit, the universe would lose its matter, until only radiation and the lightest particles drifted through the void. If protons endure, then those husks remain. Cold rocks drift, black dwarfs persist, neutron stars hold their mass. The universe would remain dotted with frozen matter, though spread so thinly across the void that they almost never touch. Either way, the direction is the same, toward stillness, toward evenness, toward the slow settling of all differences. It is striking to think how such tiny particles decide the fate of everything. Galaxies, stars, planets, life, all are built from protons. If they are eternal, the universe holds on to its matter. If they are not, the universe lets go. The grand arc of the cosmos rests on the patience of a particle so small you cannot see it. Even if protons endure, the universe in the dark era is profoundly different from what we know. No galaxies gather, no stars ignite, no planets glow with reflected light. The objects that remain are locked in silence. Their heat has radiated away, their orbits have grown meaningless, their structures isolated. Space stretches between them so far that encounters become impossible. To hold this image, picture a field scattered with pebbles. At first, the pebbles are close, you can walk from one to another. Then imagine spreading them wider so each pebble sits miles from its neighbor. Then wider still so they are separated by continents. Finally, so far that no one pebble ever meets another again. That is the state of matter in the dark era, protons intact or not, scattered so thinly that the universe is effectively empty, but time does not stop. Even in silence, even in thinness, the arrow of entropy points forward. Radiation continues to stretch as the universe expands. Photons lose energy, their wavelengths growing longer and longer until their presence feels more like background than brightness. Neutrinos, already ghost-like, drift endlessly without interaction. Space cools further, approaching absolute zero, though never quite reaching it. What does it mean for the cosmos to grow colder? You can think again of a cup of tea left in a cold room. At first, it steams, energy flowing rapidly outward. Then the steam slows, the cup cools, and soon it feels the same as the air. The universe follows the same path. At first, the difference between stars and space is immense. Later, the difference shrinks. In the dark era, the difference is nearly gone. The cosmos feels like a cup of tea long since cooled, sitting forgotten, its warmth lost to the room. If protons decay, this cooling and thinning is absolute. Nothing solid remains, only radiation stretched thin, too weak to warm, too even to drive change. If protons endure, the difference is only that some matter remains, drifting cold. In either case, the universe feels the same, empty, dark, and balanced. This may sound final, yet there is something strangely poetic in it. The universe does not end with a bang, it does not collapse into fire, it does not rage or roar, it simply spreads, evens, and quiets. What began as a great burst of light ends as a soft stillness, a fading of differences until nothing is left to shift. It is worth remembering that this is not a tragedy. To us, endings often feel sad because we measure time on human scales, but the universe is not human. It follows laws, steady and calm, carrying everything toward balance. What feels like loss is simply the last chapter of a story written from the first moment. The heatdeath is not failure, it is completion. Still, as you let this sink in, you may feel a quiet weight. To imagine everything gone, even the atoms themselves, is unsettling. Yet it also brings perspective. You exist in a universe full of light, warmth, and structure. You breathe air made of atoms. You see stars that burn. You live on a planet warmed by a sun that still glows. Knowing that this will not last forever sharpens your sense of now. It turns the ordinary into the extraordinary, the everyday into the rare. And so the path continues. Protons may endure or they may not. If they do, then matter drifts forever. If they do not, then matter dissolves and the universe becomes pure radiation. In either case, entropy wins, balance spreads, and the story stretches forward. If protons do decay, then the universe eventually loses the very substance of matter itself. Atoms crumble, planets dissolve, and even the remnants of stars become nothing more than radiation and lighter particles. What began as galaxies, stars, and worlds ends as a thin mist of energy spread across space. If protons endure, then matter persists, but scattered so far apart and cooled so completely that it no longer changes. Either way, The universe drifts into an age where only the faintest traces of energy remain, stretched thinner and thinner by expansion. This is sometimes called the radiation era, though its name can be misleading. When we think of radiation, we often imagine intense beams of light, X-rays or gamma rays bursting with energy. The radiation of this era is the opposite. It is light stretched until it is weak, long, and nearly invisible. Photons drift endlessly, their wavelengths growing as the universe expands, their energy fading toward nothing. The cosmos is not bright with beams, but quiet with a faint haze that barely counts as light at all. Think of sound fading in a large hall. At first, a note fills the space, echoing strongly from wall to wall. But as it fades, the echoes grow softer, weaker, until they are less than whispers, and finally silence. Radiation in the far future behaves the same way. What began as powerful bursts of light from stars and galaxies stretches across the expanding fabric of space until it is too thin to stir anything, too faint to matter. Even so, it is still there. Space will not be completely empty, not even in this age. A few photons remain from every star that ever burned, from every galaxy that ever shone, from every black hole that ever evaporated. They fill the universe like a faint afterglow, a memory of all that has passed. The difference is that they no longer power change, they no longer drive motion or fuel new stars. They simply drift endlessly without effect. Alongside photons are neutrinos, particles that are almost ghost-like. Neutrinos barely interact with matter even now. Trillions of them pass through your body every second unnoticed. In the far future, they too drift endlessly, so detached from everything else that they may as well be invisible. They are there, but they make no difference. They are witnesses to the fading, but not participants. Electrons, if protons endure, will remain bound to whatever matter survives. They will cling to husks of atoms, but those husks will be scattered so thin that the universe is effectively a desert of silence. If protons decay, then electrons vanish with them, leaving only the lightest particles drifting. And so the universe in this age is like a canvas that has been painted, erased, and painted again, until finally the surface is blank. Not blank because it never held anything, but blank because what it once held has stretched so thin that the differences are gone. The picture is still there, but only faintly, like pencil marks rubbed nearly clean. The expansion of space continues through all this. As the universe stretches, particles grow farther apart and radiation cools further. Today, we already see this in the cosmic microwave background, the faint afterglow of the Big Bang. It began as searing light, brighter than any furnace, but it has stretched over billions of years until it is now just a dim microwave glow, barely 3 degrees above absolute zero. In the far future, even that glow fades further, until it becomes radio waves stretched beyond usefulness. To imagine this, think of a balloon being inflated. At first, the markings on the surface are close, bright, and clear. As the balloon grows, the markings stretch, thin, and fade. Eventually, they become so faint that you can barely tell they were ever there. That is how light behaves in an expanding universe. Every photon stretches, every wave grows longer, every memory of brightness becomes a faint shadow. In the radiation era, entropy is nearly complete. There are no strong differences left to smooth out, no steep gradients to flatten. The universe is almost balanced, almost even, almost resting. Time, though, still ticks. It ticks so slowly, so quietly, that it hardly feels like motion anymore. And yet it continues because physics does not stop. This raises a deep question. What does it mean for time to flow when nothing happens? We are used to time marked by events. The earth spins, the sun rises, a clock ticks, a candle burns. Each of these is a way of measuring change. But when stars are gone, when black holes have evaporated, when even particles drift too far apart to interact, how do we mark time? In one sense, time still exists, written into the equations of physics. The The particles still move, the universe still expands, entropy still increases. But in another sense, time loses its meaning. Without change we can see, without events to measure, time becomes an abstraction. It is not felt, it is not lived, it simply is. This thought can feel unsettling because we experience time through change. A heartbeat, a sunrise, a spoken word, each is a marker of time moving. In the radiation era, there are no such markers. Time is stretched so thin that it feels like silence, like waiting without end. And yet there is also a strange beauty in it. The universe does not end with chaos, but with calm. It does not roar, it rests. The radiation era is the softest of chapters, a place where energy is spread so evenly that nothing more can happen, and the cosmos simply exists in balance. Whether protons decay or not, the overall picture is the same. Matter dissolves or matter persists, but in both cases it makes no difference. Entropy wins, energy spreads, and the universe becomes a place where silence reigns. It is worth pausing on what this means for us now. We live in a time when stars shine, galaxies glow, and energy still flows. The heat death may be written in the laws of physics, but it is far away. We are alive in the bright noon of cosmic history, in the rare moment when difference still drives creation. That makes this moment extraordinary, even if it feels ordinary to us. And so the story drifts on. From stars burning to remnants cooling to black holes evaporating to particles spreading, the trend is steady. Each stage is slower than the last, each quieter, each more even. By the radiation era, the pace is so slow and the silence so deep that it feels like the universe has stopped. But it has not stopped. It is still moving, still balancing, still evening out. And beyond even this, there is still more to ask. If the universe becomes nothing more than a thin sea of drifting radiation, is that truly the end? Or does something unexpected emerge from the silence? That is a question that belongs to the farthest reaches of physics, and perhaps to imagination. For now, the path is steady. Energy spreads, differences fade, and the cosmos glides toward its long rest. In the deep silence of the radiation era, the universe has stretched so far and cooled so much that nearly all differences are gone. Photons drift with wavelengths longer than galaxies. Neutrinos pass invisibly, rarely touching anything. If protons decay, then matter itself is gone, leaving only radiation. If protons endure, then faint husks of matter remain, but scattered so thinly that they are effectively absent. What fills the cosmos is not structure, but emptiness. And yet, it is an emptiness that still carries traces of what once was. Every photon that drifts now is a memory of some event in the distant past. Some were born in the early fire of the Big Bang. Some came from the burning of stars. Some are the last sighs of black holes evaporating. All are stretched, all are weakened, but they are still there. The universe is like a museum of whispers, every photon a record, too faint to read. The temperature of space continues to fall, not sharply, but steadily, as expansion stretches every wave. From 3 degrees above absolute zero today, it falls to fractions of a degree, then to fractions of fractions. The approach to absolute zero is infinite. The universe can never quite arrive because every step is only another fraction closer, but the effect is the same. Motion slows, interactions fade, silence deepens. What does absolute cold mean for the cosmos? It means that no particle has enough energy to stir another. No collisions happen, no sparks ignite. It is as though every flame, every fire, every motion has been drained, leaving only the faintest drift. Physics still rules, but physics has nothing left to push. And yet, the equations of quantum mechanics hint that even in emptiness, fluctuations can occur. The quantum world is not perfectly still. It jitters, it flickers, it allows brief appearances of energy, particles rising and vanishing again in tiny blinks. These are not the kind of events that light up galaxies, but they are real. Even in the void, quantum fluctuations remind us that silence is never perfect. Could such fluctuations change the fate of the universe? Some thinkers suggest that over infinite time, they might. A fluctuation could, in theory, create new energy, even a new universe. Others argue that such events are so rare and so improbable that they do not matter in practice. Either way, the thought lingers. In the deepest silence, perhaps a spark still glimmers, hidden in the jitter of the quantum vacuum. But whether or not fluctuations matter, the path of entropy remains. Balance is the destiny, and the cosmos continues its drift toward it. Each photon stretches further, each particle separates more, and the canvas of space becomes smoother. The fluctuations, if they occur, are only ripples on a still pond, too small to disturb the picture. The meaning of time in this era becomes even more abstract. With no events, no cycles, no clocks, time loses its markers. Physics still describes it, but experience would not feel it. Time without change is like space without landmarks. It exists, but it cannot be measured in any way that feels real. If there were observers in this age, they would find themselves unable to count time at all. Minutes, hours, years. Such things depend on change, and change has gone. It helps to imagine a person waiting in a dark, silent room. At first, they feel the minutes pass. Then, as nothing happens, they lose track. The minutes blur, the hours vanish, and eventually time feels like one continuous stretch of stillness. The far future of the universe is like that room, stretched to infinity. Time passes, but it feels like nothing. Expansion continues through all of this. Galaxies have already been torn apart, stars are gone, black holes have evaporated, but space itself still swells, carrying the faint traces of radiation wider and wider. Eventually, expansion moves so fast that each particle is cut off from the others. Every particle becomes its own isolated universe, unable to see or touch another. The horizon shrinks around each until its view of space is empty. The ultimate loneliness is not only separation, but isolation so complete that no particle knows another exists. This picture is difficult to hold because it is so unlike the universe we know. We live in a cosmos filled with light, with galaxies in every direction. Even now, when most of the universe is empty, we see richness everywhere. In the far future, richness is gone. What remains is nothing but emptiness, filled with particles so thin and so separated that they might as well not exist at all. And yet this emptiness is not destruction, it is not fire, it is not collapse, it is balance. The second law of thermodynamics has finished its work. All gradients are gone, all differences smoothed, all energy spread. The universe has achieved its final state, not in rage, but in rest. For some, this thought is unsettling. To imagine a cosmos without stars, without life, without change feels like loss, but it can also be seen as completion. The universe began with imbalance, a hot, dense state full of difference. It unfolded through galaxies, stars, planets, and life. Now it rests, balanced and calm. It is the closing of a cycle, the stillness after the storm. There is a quiet poetry in this. The heatdeath is not the destruction of the universe, but its evening out. It is the long exhale after the long inhale of creation. What began in fire ends in silence. What began with difference ends in balance. The symmetry is stark, but also beautiful. And yet questions remain. Could the quantum vacuum seed new beginnings? Could fluctuations give rise to fresh bursts of energy? Could our universe, quiet and still, be only one chapter in a larger cycle? These questions reach beyond what we know, into the realm of speculation. Physics answers carefully, but imagination stretches further. The truth is that we do not yet know whether silence is final. For now, the picture is simple. The universe has grown old, it has spread its energy thin, it has lost its structures, its fires, its engines. What remains are particles, drifting endlessly, stretched by expansion, cooled by time, balanced by entropy. The cosmos has reached its stillness, and it rests there, patient and eternal. The silence of the far future stretches on, and with it comes the strange realization that time itself may have lost its usual meaning. We think of time as a sequence of events, but in a universe where events no longer occur, time becomes less like a flowing river and more like an endless ocean, still and featureless. The particles that remain, photons, neutrinos, and perhaps the last survivors of protons, drift endlessly, but their drift is so slow and so spread that it no longer creates markers of change. The expansion of space continues, carrying these faint particles farther and farther apart. What was once a connected cosmos has become scattered to the point of isolation. Each particle exists within its own horizon, cut off from all others by the relentless stretching of space. The scale of separation grows so vast that for all practical purposes, each fragment of matter or energy lives in its own private universe. To picture this, think of a vast plain at night, once filled with campfires, each one lighting a circle of ground. At first, the fires are close enough that their light overlaps, creating warmth and connection. Over time, the fires go out, one by one, until only a few embers remain, far apart. Finally, even the embers fade, and the plain is swallowed in darkness. That plain is the cosmos, and its last faint embers are the scattered particles drifting alone. In this endless night, physicists ask what it means for time to continue. If nothing changes, does time still pass? The laws of physics say yes. The expansion of space still unfolds, entropy still creeps higher, and the equations still run forward. But to an observer, if one could exist in this emptiness, time would feel meaningless. There would be no rising or falling, no cycles, no events to mark the passage. It would be as if eternity had collapsed into stillness. And yet, physics also whispers that stillness may not be perfect. At the scale of the very small, quantum mechanics does not allow absolute silence. The vacuum is not empty, but restless. It flickers with fluctuations, tiny blips where particles appear and vanish again. Normally, these fluctuations are too small, too brief to matter. But when stretched across infinite time, even the smallest probability becomes a possibility. This idea has given rise to speculation. Over unimaginable spans, could quantum fluctuations stir something new? Could they create rare, isolated events? Could they even, in some far reach, spark a new universe? These are not certainties, but possibilities, drawn from the strange rules of the quantum world. Some physicists describe a concept called vacuum decay, where the universe could, in theory, tunnel into a lower energy state. If such a thing occurred, it could create a new burst of energy, a kind of rebirth. Others imagine quantum fluctuations giving rise to baby universes, pockets of space that inflate and become new realities, separate from our own. These ideas are speculative, resting at the edges of what we know, but they offer a reminder that even in silence, the story may not be finished. To bring this closer, think of a field of snow. At first it is smooth and still, a perfect white sheet. But if you wait long enough, you notice tiny shifts, a patch settling, a crystal glinting. The snow is not truly frozen in perfection, it still moves in ways almost invisible. The late universe may be similar. It seems smooth, but at the smallest scales, tiny shifts could ripple through the silence. Still, whether or not such fluctuations occur, they do not change the broad picture of heat-death. On cosmic scales, entropy continues to climb, differences continue to vanish, and balance continues to deepen. The universe glides toward a state where nothing new can happen, and any flicker that does occur is swallowed in the vast stillness around it. This thought can feel bleak, but it can also be seen as peaceful. The cosmos is not ending in catastrophe, but in rest. It is not exploding, not collapsing, but settling into balance. What began as a storm of fire and structure ends as calm, as evenness. That symmetry is as beautiful as it is quiet. The numbers involved in this age stretch so far beyond imagination that they begin to lose meaning. Spans like 1 to 100 years, 1 to 1,000 years, even longer, pile zeros upon zeros. Our minds cannot truly hold them. To us, 100 years feels long, 1,000 ancient, 1,000,000 unreachable. 1,000,000,000 years dwarfs all of human history. But the universe continues far beyond billions, trillions, quadrillions, into spans so long that the human brain must surrender, must accept that these numbers describe a patience beyond comprehension. What is remarkable is that physics remains steady across these spans. The same laws that govern your cup of tea cooling or your ice melting also govern the slow fading of galaxies, the evaporation of black holes, the drift of photons. The scale is vast, but the principle is simple. Energy spreads, differences vanish, entropy rises. That quiet rule carries the universe from fire to silence, without pause, without exception. Consider how strange this is. The same law that explains why your room cools when the window is open also explains why the universe itself cools across trillions of years. The ordinary and the cosmic are bound by the same truth. It shows us that the story of the cosmos is not alien, but familiar. It is written into the small moments of everyday life. And so, the heat death of the universe is not only a tale of physics, but a tale of perspective. It is a reminder that the laws we live with, heat flowing, differences fading, extend to the very largest scales. The difference between your cup of tea and the cosmos is not the law, but the scale. The cup cools in minutes. The universe cools in eternities. The thought of eternity in silence may feel heavy, but it can also bring a kind of comfort. If the cosmos rests, then everything it has carried, stars, galaxies, life, thought, was part of a story that ended in peace. It is not destruction, it is closure. The balance reached at last. As expansion carries particles farther apart and radiation stretches beyond meaning, the universe becomes what it was always heading toward, a place without difference, a place without gradient, a place where entropy has done its work fully, a place of stillness vast and complete. As the universe drifts deeper into balance, the meaning of time becomes harder to hold on to. Time is not an object, it is not something you can point to, but something you feel through change. The tick of a clock, the orbit of a planet, the burning of a star, all of these give rhythm to existence. In the far future, when stars are gone, when galaxies no longer gather, when even black holes have faded, that rhythm disappears. Time becomes something without a beat, a silent stretch where nothing stirs. The equations of physics still track time. Expansion continues, entropy rises, particles drift. But for an observer, if one could exist in such stillness, time would no longer feel like motion. It would feel like a horizon without features, a vast plain without landmarks. The days, the years, the ages would blur into one continuous stillness. Imagine walking in a desert with no sun, no stars, no mountains, nothing to guide you. Step after step, the landscape never changes. You move, but you cannot tell that you are moving because everything looks the same. That is the nature of time in the heat death of the universe. It is not gone, but it is featureless. This raises a strange question. Can time exist without events? To us, the answer feels uncertain because time is inseparable from experience. We know it through change, but physics separates the two. Time is a dimension, like space, and even if nothing happens, time still unfolds. The difficulty lies in imagining it, because human minds evolved to feel time through cycles. Without cycles, without events, our intuition falters. What deepens this strangeness is the concept of forever. We use the word easily, forever waiting, forever silent. But in the context of the universe, forever means numbers so vast they dissolve meaning. 1,000,000 years feels long, 1,000,000,000 years stretches imagination, 1,000,000,000,000 years overwhelms. But the heat death is not measured in trillions. It is measured in spans like 100 years, 101,000 years, and beyond. These are numbers so large that even metaphors fail. Forever, in this sense, is not only long, it is incomprehensible. You can try to hold it with a picture. Imagine writing one digit every second. You could live a lifetime, and you would not come close to finishing. You could live the age of the universe itself, and you would not come close. And yet the universe stretches into numbers even greater. Time, in this sense, is not something we can picture, but something we must surrender to. The silence of the far future is not absolute nothing, but it is close. Radiation remains, but it is stretched into waves so long they are meaningless. Neutrinos remain, but they pass without contact. Perhaps protons remain, drifting as frozen husks. Perhaps they decay, leaving only radiation. In either case, the silence is deep. Nothing stirs, nothing gathers, nothing changes in ways that matter. The story of difference has ended, and yet, even in this silence, the memory of the past is carried in the smallest traces. Each photon, however faint, is a record of something that once happened, a star that once burned, a black hole that once evaporated, a galaxy that once collided. The universe may no longer hold structure, but it holds echoes. The silence is filled with faint reminders, though they cannot be read. This makes the heat death both final and strangely incomplete. Final, because nothing new can emerge. Incomplete, because the past still lingers faintly, scattered in the drifting particles. The cosmos never erases itself entirely. It only spreads its story so thin that the story can no longer be told. Some thinkers suggest that in such vast spans of time, the rarest events might occur. Quantum fluctuations, brief flickers of energy, could appear even in the vacuum. Over infinite spans, they might even produce strange outcomes, like a self-assembled particle or a fleeting bubble of energy. These possibilities are speculative, and they do not change the broad picture of silence, but they remind us that stillness is never perfect. The quantum world always jitters, even in emptiness. This idea leads to another speculation, the so-called Boltzmann brain. In theory, over infinite time, random fluctuations could assemble particles into a brief, conscious mind, a brain that appears from nothing, thinks for a moment, and dissolves. This is not likely in any practical sense, but in infinite time, the improbable becomes possible. Some physicists find this unsettling because it raises questions about what counts as existence. But for the heat death, it is only a curiosity. The overall silence remains. What matters most in this stage is that entropy is complete. The universe has no gradients left. Energy is spread evenly. No more heat flows, no more stars ignite, no more galaxies collide. The arrow of time has reached its destination. What began with imbalance has ended in balance. For us, who live in a universe filled with change, this end feels almost alien. We are used to cycles, days, years, lifetimes, histories. The idea of time without cycles is hard to hold, and yet this is the destiny of the cosmos. Not destruction, but stillness. Not collapse, but quiet. Not chaos, but balance. It can be humbling to reflect on this. The vastness of the universe, its galaxies and stars, its planets and lives are temporary. They are extraordinary, but they are not eternal. And yet, that temporariness makes them more meaningful. The beauty of a starry sky lies not only in its light, but in knowing that it will not always shine. The beauty of life lies not only in its motion, but in knowing that it is rare. And so, in the far future, when all has settled, the universe will not be tragic, but complete. It will not roar, but rest. The heat death is not a failure of creation, but the fulfillment of its laws. It is the last chapter in the longest story ever told, a story that began in fire and ends in silence. As the universe moves deeper into the far future, the silence that defines the heat death becomes its most striking quality. Silence not only in sound, because space has always been without sound, but silence in change itself. No new stars form, no galaxies collide, no planets orbit with warmth. The great cycles that once gave rhythm to the cosmos have all ended, leaving a vast expanse where stillness reigns. This silence is not sudden, but gradual. It is the result of processes that began long ago, in the very first moments of the Big Bang. Back then, the universe was full of imbalance. It was hot in some places, cool in others. It was crowded with matter, clumped into clouds, which collapsed into stars, which forged new elements. The story of everything you know, stars, galaxies, life, thought, is the story of imbalance working itself out. Energy flowing from hot to cold, differences smoothing away. Now, in this age, the smoothing is nearly complete. Entropy has done its work. Energy has spread so thin that there are no gradients left to drive change. Imagine walking downhill until the ground flattens. At first, every step moves you lower. Then the slope softens. Finally, the ground becomes flat and you can walk forever without changing height. That is entropy in the heat death. The downhill flow of energy is finished, the slope is gone, and the universe lies flat. The expansion of space continues, though it no longer creates visible difference. Distances grow, horizons widen, but what lies between them is emptiness. Each photon stretches further, each particle drifts wider, until the separation is absolute. In a practical sense, each particle lives in isolation. It can never meet another, never share its faint trace of energy. The cosmos becomes not a sea of particles, but a scattering of islands, each alone in an endless void. To us, who live in a universe full of connection, this picture is hard to hold. Our lives are woven from cycles and interactions. The earth spins, the sun rises, seasons turn, generations follow one another. Even at larger scales, galaxies cluster, stars orbit one another, planets pull on moons. Connection is everywhere. But in the late universe, connection disappears. Expansion pulls everything apart, entropy drains every difference, and the fabric of reality itself grows lonely. In such a place, what does it mean for time to continue? The equations of physics say that time flows, that entropy still ticks forward, that expansion still stretches. But without events to measure, time feels less like flow and more like endless duration. Imagine sitting in a quiet room, waiting, with no clocks, no windows, no sound. After a while, you lose track of minutes, hours, days. The difference between one moment and the next dissolves. The universe, in its final age, becomes that room. Time continues, but it feels like stillness. It is worth pausing to notice how strange this is. The same physics that makes your tea grow cold also drives the universe into silence. The same second law of thermodynamics that explains why ice melts, explains why galaxies fade. The laws are the same, only the scale is different. The small, familiar changes of daily life are echoes of the great changes that shape cosmic destiny. This connection is humbling. It shows us that the fate of the universe is written in every ordinary moment. Every time you see warmth flow into cold, every time you see order dissolve into disorder, you are watching the same rule that carries galaxies into silence. The laws that shape the end of the cosmos are not distant, they are already here. Some thinkers have tried to imagine whether anything could break this silence. Could quantum fluctuations stir something new? Could the vacuum shift, releasing new bursts of energy? Could there be cycles where universes end and begin again? These ideas remain speculation, hints at possibilities beyond what we know. But whether they are true or not, the story of heat death is still the story we can follow with certainty. Entropy rises, energy spreads, and balance deepens until silence is complete. The possibility of quantum fluctuations adds an odd detail to this picture. Even in silence, the vacuum is restless. Particles appear and vanish in tiny blips, too small to matter. Over infinite spans, unlikely events could occur. Some imagine entire universes sprouting from these fluctuations. Others imagine smaller curiosities like random patterns of particles or even fleeting consciousness. These ideas are curious, but they do not change the broad canvas. They are sparks that flicker and vanish in a night that stretches without end. If anything, they remind us that stillness is never perfect. At the smallest scales, the quantum world always flickers. But on the scale of the universe, these flickers are so rare and so small that they cannot disturb the silence. The heat death is not undone by them. It remains the calm end of difference. For us, living in a universe full of movement, this ending can feel bleak. But it is not destruction, it is completion. It is not collapse, it is rest. The universe does not end in fire, it ends in balance. That balance is the natural consequence of laws that have always been at work. It is not a tragedy, it is a symmetry. What began in a burst of energy ends in its quiet spreading. What began as imbalance ends in evenness. And there is something comforting in that symmetry. It means that nothing is wasted. Every star, every life, every thought, every moment was part of the same unfolding, part of the same drift toward balance. The universe did not fail, it simply finished. The silence is not emptiness, it is completion. In thinking about this, you may notice that the heat death of the universe is also a mirror for our own lives. We too move from imbalance to balance. We too carry energy that fades, cycles that end, differences that smooth. Just as the universe finds stillness, so do we. The parallel is not perfect, but the reflection is there. The same laws that govern the stars govern us. We are part of the same story, and so the heat death becomes not only a cosmic idea but a personal one. It reminds us that everything changes, that everything fades, that everything rests. It asks us to see our moment, our brief moment in a universe still bright, as extraordinary, to see the light around us not as ordinary, but as rare, to see our lives not as endless, but as meaningful because they are brief. The far future is silence, but the present is light. That contrast gives weight to now. It tells us that this age, when stars shine and galaxies glow, is a precious age, that we live in the noon of cosmic history, a moment that will not come again. The silence of the future does not diminish this moment, it deepens it. It reminds us to look at the stars above and see them not only as distant suns, but as brief fires, precious and rare. It reminds us to see our days, our lives, our histories as part of the same unfolding, temporary but extraordinary. The heat death of the universe is the end of difference, but it is also the completion of a story that began in brilliance. It is the final symmetry of a cosmos that has always been guided by the simplest of laws. Energy flows, differences fade, entropy rises. From those three truths comes everything: galaxies, stars, planets, life, thought, and silence. In the farthest reaches of time, when everything familiar has faded, the universe becomes simple. Not simple in the way of clarity, but simple in the way of stillness. No galaxies shine, no stars burn, no planets orbit with warmth. The great engines of creation are gone, their fuel spent, their motions ended. What remains is silence. That silence is not empty, though it may feel that way. Particles still drift, photons still stretch, neutrinos still pass without touching. If protons endure, faint husks of matter remain. If they decay, then even those husks dissolve, leaving only radiation spread so thin that it barely counts as presence. The difference between the two outcomes matters little. Either way, the universe is still. Entropy has reached its summit. Energy has spread so evenly that there are no gradients left. Without gradients, there is no flow. Without flow, there is no change. Without change, time itself feels hollow. It exists in the equations, but not in experience. The arrow of time has arrived at its horizon, and there it rests. Think of a candle that has burned down to nothing. At first it glows, it flickers, it warms the room. Then the flame shrinks, the wax melts away, the light dims. Finally, only smoke lingers, then even that fades. The room is dark and the candle is gone. The universe is that room, stretched to infinity. The light has burned, the warmth has spread, the story has ended. But this ending is not tragedy, it is not catastrophe, it is not collapse, it is completion. The heat death of the universe is the final balance, the natural consequence of the laws that have guided everything from the beginning. It is not failure, it is fulfillment. What began in fire ends in rest. What began with imbalance ends with evenness. And so the universe rests, quietly, endlessly, patiently. No more stars are born, no more galaxies collide, no more black holes feed. Only the slow drift of silence stretched across eternity. If time continues, it continues without rhythm, without cycles, without markers. It is not a river, it is an ocean, still and endless. This picture can feel unsettling because it is so far from the world we know. We are creatures of motion and difference. We feel time through change. We live through cycles. We mark our lives by beginnings and endings. A universe without change feels alien, but it is also inevitable. The same laws that cool your tea, that melt your ice, that guide your breath, guide the cosmos into silence. The small and the vast are bound by the same truth. And yet, this silence carries a quiet beauty. It is the balance that everything has always moved toward. It is the fulfillment of entropy, the last chapter written by the second law of thermodynamics. It is not loud, but it is complete. It is not bright, but it is perfect in its symmetry. There may be whispers of something beyond, quantum fluctuations that stir, creating sparks in the vacuum, speculations about new universes budding from the old, possibilities of cycles, rebirths, beginnings hidden in the silence. But those belong to imagination, not certainty. The story we can follow is the story of entropy, and that story ends here, in rest. So the universe, vast and ancient, finds its balance. It began with brilliance, unfolded into structure, gave rise to galaxies, stars, planets, and life. It carried difference, and from difference came everything. Now it rests, and from rest comes nothing more. The heat death is not an event, it is a state, and once reached, it endures without end. This is the great symmetry. The universe that began with fire ends in quiet. The universe that was filled with imbalance ends in balance. The universe that was alive with change ends in stillness. It is not dramatic, but it is true, and in its truth there is peace. For us, living in the brightness of the cosmic noon, this story is both humbling and uplifting. Humbling because we see that everything we know is temporary, fleeting, bound by laws larger than ourselves. Uplifting because it reminds us that our moment is rare. We live in a universe where stars still shine, where planets still orbit, where life still stirs. We live in a time that will not come again. The silence of the far future does not diminish this. It makes it more precious. Every star in the night sky is not just a light, but a brief fire in a story that ends in quiet. Every day you live is not just ordinary, but extraordinary, because it happens in the rare age of motion. Every breath you take is a small miracle, carved from imbalance, powered by difference, possible only because the universe is not yet still. When the silence comes, it will come gently. No collapse, no explosion, no roar. Only stillness spreading until it is complete. The cosmos will rest, and in that rest, the story of everything will be finished. And so, as you listen, let this picture become not something heavy, but something calming. The universe is vast, and its laws are steady. What feels like an ending is only balance, only completion. It is the quiet exhale of a story that began in brilliance. Let your mind drift with it, gently into the silence. Let the thought of balance soothe you, as though you, too, are part of the same stillness, because you are. You are made of the same matter, guided by the same laws, carried by the same story. The end of the universe is not separate from you, it includes you, and in that truth there is peace. Now, as the universe rests, you can rest too. Close your eyes, let the silence carry you, let the stillness deepen. The story of the cosmos is vast, but tonight it has carried you gently into quiet. And just as the universe finds its balance, so can you.